Believe it or not, everything you see, everything you are, it's all built from a blueprint that's almost entirely empty space. So today, we're going to deconstruct that blueprint, the atom.
So let's start with a really big question. Just look around you for a second. The screen you're watching this on, the chair you're sitting in, your own hand. What is all of this really made of? What's the fundamental stuff? You ready for this? The answer is mostly nothing. I know it sounds completely crazy, but one of the wildest facts in science is that the solid world we see is pretty much an illusion. Because the building block of all matter, the atom, is almost entirely empty space.
This quote just nails the perspective perfectly. I want you to picture it. You're standing in the middle of a gigantic football stadium. That entire stadium is the size of one atom, and all of its mass, pretty much everything that actually has weight, is right there in the center, and it's no bigger than a single pea. The rest? Just empty space. Wild.
Okay, so if it's mostly empty, what's actually in there, in that vast emptiness in that tiny little core? Well, let's meet the three key players that make up the atomic blueprint.
Here they are, our subatomic all-stars. You've got the heavyweights, the proton, which has a positive charge, and the neutron, which has no charge. They're the ones with all the mass. And then you have the electron, this zippy little particle with a negative charge and a mass so tiny it's practically negligible in comparison.
So how does this all fit together? It's simple, really. All the heavy stuff, the protons and neutrons, get crammed together into that super dense central core we call the nucleus. And all that empty space, that's the electrons' turf. They exist out there in regions called shells, held in place by the magnetic pole of that positive nucleus.
Now you might be picturing these electrons just buzzing around randomly like a chaotic swarm of bees. But nope, their location is incredibly organized. And understanding that organization, that's the key that unlocks pretty much all of chemistry.
Electrons have to live in specific energy levels, or shells. The easiest way to think about it is like an apartment building. The ground floor, which we call n equals 1, is closest to the nucleus and has the lowest energy. As you go up to higher floors, n equals 2, n equals 3, the electrons living there have more and more energy.
So to really find an electron, we need its specific three-part address. The shell is like the city it lives in. The subshell is the street, and the orbital is the actual house. And just like a real house, it's got a limited capacity.
And you better believe this neighborhood has rules, strict ones. First, electrons are kind of lazy. They always take the easiest spot available, the one with the lowest energy. Second, each house, or orbital, can only hold 2 electrons, and they have to be opposites. We call it having opposite spins. And finally, if there are multiple empty rooms on the same street, electrons will take their own room first before they're ever forced to pair up.
And when you apply all those rules, what do you get? You get a specific address for every single electron in an atom. This right here, this is basically the complete address book for an iron atom. It tells us exactly how all 26 of its electrons have filled up the available spots, all according to those laws of nature.
Okay, so we've built our atom. We know where everything lives. Now for the fun point. How hard is it to mess with it? What's the price we have to pay to steal one of its electrons?
And yeah, there's a technical name for that price. It's called the first ionization energy. Put simply, it's the amount of energy you need to exert to go in and pluck that outermost, most loosely held electron away from its atom.
Now check this out, because this is where the story gets really good. Look at the data for magnesium. Removing the first electron costs 736 units of energy. The second one costs about double, 1450. Makes sense. But then, look what happens when we try to remove the third one. Whoa! The price skyrockets to over 7,700. That's not just a small jump, that's a massive leap. So what's going on there? Why does it suddenly get so incredibly expensive to remove that third electron? That huge jump, it isn't a mistake. It's a clue, a breadcrumb trail that leads us right to the atom's secret structure. And the answer brings us right back to those shells, to the floors in our atomic apartment building. See, the first 2 electrons we took from magnesium, they were on the outer shell, the top floor. Easy pickings. But that third electron? To get that one, you have to break into a lower floor, an inner shell that's completely full, stable, and much, much closer to the powerful pull of the nucleus. You're not just taking an electron anymore, you're trying to break into the atom's high-security vault. And it's this exact kind of evidence, these predictable, massive jumps in energy, that gave scientists the proof they needed for the shell's structure of atoms. The whole concept is visualized perfectly in the most iconic chart in all of science. I mean, just look at it.
The periodic table is so much more than a list of elements you had to memorize in school. Its whole design, the rows, the columns, the blocks, it's a direct map of the atomic blueprint we've been talking about. It's the ultimate cheat sheet.
And those energy prices? They follow these beautiful, predictable trends right on the table. As you go across a row, the price to remove an electron generally goes up. Why? Because the nucleus is getting more positive and pulling its electrons in tighter. But as you go down a column, the price goes down. You're adding more shells, more floors to the building, so that outer electron is way further out and much easier to just pluck off.
And that just leaves us with this one incredible thought. The entire universe, in all its mind-boggling complexity, is built on a foundation that's mostly empty space, all governed by a few simple, elegant energy rules. Everything we see and touch comes from this. The simple blueprint of the atom is literally the blueprint for reality itself.